So what we now know about definite integrals gives us kind of a convenient way of writing the solution to an initial value problem, and I just want to show you what that is. So let's suppose that we know that dy over dx, or sometimes it's written as y prime, is equal to some function of x. And we know the initial value. We know that at x equals a, the value of y is going to be b. That's what this expression is saying. Then we can write that y is equal to this function. This is we can write it as an integral. Write y as the integral from a to x of f of t dt, and then after you calculate that, or after you express that, you add b. The truth is, you're not going to calculate this value. You're simply going to express that part of the function in this form. One way to look at it is that y is equal to, if you want to think of it in words, y is equal to the integral from the initial known x value, that's a, up to x, of f of t dt, and then plus, this is a plus sign, plus the initial y value, which of course is b. Like anything else in this class, the abstract words are more complicated than the example, so let me just show you a specific example. So let's suppose that dy over dx, or I could have written, by the way, I could have written y prime is equal to 1 over x. I could have written this either way. So let's suppose that dy over dx is equal to 1 over x, and y of e over 2, y of e squared is equal to 5. In other words, once I know what this statement means is that once I've figured out what y is, if I plug in e squared as the x value, I'm going to get 5. So let's find y. Well, using this formula, what we can see is that a is equal to e squared and b is equal to 5. Therefore, the answer is going to be y equals the integral from e squared to x of 1 over t dt plus 5. Where I should have written this here, that of course f of t is going to be 1 over t, because we know that f of x is, in this example, this is f of x. Remember, we're given dy over dx equals some function of x, so mapping that on to what I said about the general rule, we're given dy over dx equals f of x, so this 1 over x is the f of x. One way you can think of it is you simply take whatever is after the dy over dx and just replace it with t. That's what you're going to put after the integral sign. Okay, now let's just verify that this actually gives us the same answer that we would get if we had solved this the old way. So let's suppose that I was simply given this problem and I didn't know this technique, and I would have solved it the other way. So what I would say is f of x equals 1 over x. ln absolute value of x is an antiderivative of 1 over x. And then what I'd say is, therefore, ln of x plus c has to equal 5 when x equals e squared. So I would solve for c that way. I would plug in e squared and try to solve for c. I'd say ln of e squared plus c equals 5. That gives us ln of e squared is 2 plus c is equal to 5, and therefore c is equal to 3. So the function I'd be looking for is y equals ln x plus 3. So that's our function. Now the question is that equivalent to the function that we found up here? And I'm going to show you why it is. So let's suppose that I take this function here and I actually just evaluate it. I'm going to get y equals the integral of 1 over t dt is ln t. So y equals ln t going from e squared up to x, and then we still have this plus 5 at the end that I'm going to have to add in. So that's going to be, I'm going to plug in x and e squared and subtract. That's going to give me ln of x minus ln of e squared, and then I still have this plus 5. So now that's going to come out to ln of x, make that a little neater, ln of x minus, we know that ln of e squared is 2, plus 5, and if I simplify that, I get ln of x plus 3. So as you can see, this solution, once I actually evaluate it, is going to come out to exactly the same solution that I would have gotten by the conventional method of solving an initial value problem. This is just sort of a more convenient way to express it. Now, I am guessing that some of you are thinking, so are you saying you want me to evaluate you want me to form it this way and then evaluate it? The answer is no. The point we're trying to make in this section is that this expression that's written here in purple is a perfectly valid way to express y, the function. There's nothing wrong with leaving this integral sign in, as long as you do it in the right way. It's got to be integral from initial value up to x, and then you replace the variable. Instead of, if you're given f of x, you're going to change it to f of t, and then write dt at the end, and then finally add the initial y value at the end. So using this way of expressing the solution to an initial value problem. I'll leave this up here.